All right. Let's just verify that these people, everybody can. Could you go ahead and talk there?
Hello, I'm talking.
All right.
What time is it anyway? The clock says 9:10.
Yeah, the clock's not. All right.
I'm like, I hope I've been here for 9 hours.
Is everybody here online? Can somebody chat back? No? Well, it should be working. All right. I'll let you get back to it. I'm not sure if it should be going now.
Anyway, so you got the idea here that we're trying to match one fine mode, one coarse mode that eventually, when combined, does the best match to the green dots. So I had a different version of this before, but we had lost the axes, but it looks like we've lost a little bit different piece of it now. One fine mode, one coarse mode, combine them together, and how close can we match the green lines? And we eventually get a solution, and that's our solution. We have a, the loading of fine, the loading of coarse that best matches that, and that's our answer. We have slightly different assumptions over land. Jorm Kaufman had discovered that, and part of it was Andy Wald, who I also had worked here. He's sitting back here. So they had papers here that looked at it looks like the arrows moved off there a little bit, but that there's relationships between if you look over dark land surfaces, that there's pretty consistent relationships between red channels and these 2.1. So that if you look at a lot of vegetated areas, the surface reflectance in the red channel is about half of the surface reflectance in the 2.1. And then the same thing with blue to red. And so if you use those as constraints, then you can now have a combination, and so I kind of show that here. So the same kind of thing, you have fine mode, coarse mode aerosols with a surface reflectance, and you add them up together, and you get a combination. And so as long as you use these constraints on the surface, and you get fine reflectance, coarse reflectance, and so that's our job over the land. And so that's what we get. So where are we now? So what we have now is a collection stick, what we call. So we had many versions of this product over the years, and now we've reprocessed such that we have something called collection 6 or collection 6.1. So we've made improvements over time, so now what we do, here's that same scene we saw before, land, ocean, and we have these sun photometers at the ground all over the place. So this is called AeroNet. There's, I don't know, something like 400 or 500 current sites around the globe. And so we've been trying, we and other folks that do aerosol retrieval algorithms are always comparing. So, in this red area, AeroNet's saying it's 0.67, in this blue area, AeroNet's saying it's 0.22, and we kind of see that. So we do this kind of global aggregation of all the comparisons, and we come up with expected errors. And it's not just a scatter plot, it's also as a function of loading as well. So we get something resembling about plus minus 0.5 plus 15% over land, and a similar, with a little bit better constraints over ocean. And so that's our product globally. That's over many years now. And then, so overall, things are matching pretty well. We're pretty happy with things. But what's fun is now we get to ask, a little more detailed questions. So we do have two of the instruments. One's over Terra, one's Aqua. They actually orbit at different times. So there's a 10:30 a.m. descending orbit for Terra, and a 13:30, so a little later in the afternoon, orbit for Aqua. Do they observe the world in the same way? How are their time series? And it's interesting that we find that there's actually a global offset between the two. So if we took global averages of Terra AOD minus Aqua AOD, you pretty much have an offset everywhere except for a few cases in these, let's say, these smoke regions. And it seems like it's consistently in more biomass burning regions where we kind of expect there to be maybe a maximum AOD in the afternoon, which you because of more fire burning. You actually see that in these few places, but almost the whole rest of the globe, the morning orbit seems to have a higher optical depth. And again, these are the same algorithms on both. And these are compared to AirNet. So now we see that Terra is biased a little higher compared to the AirNet than Aqua. And so we've been trying to ask more recently about like why this is happening. So we played some games where we were looking at a model. This is MERA 2, which is an instance of the Goddard GMAO's GEOS model. And so basically we're taking these reanalyzed meteorology where they have chemistry inside of it to do the aerosols. And so we've been saying, well, what happens, can we now aggregate the morning versus afternoon in the model? And do we get the same kind of morning versus afternoon? And so this is our Terra versus Aqua from our measurements. And this is basically sampling the model exactly like we would sample from a satellite, and saying, hey, you know what? There are places on the globe where there's differences between morning and afternoon, but globally the difference is closer to 0 than we get from the actual observations. And that's unfortunate too, is that these offsets seem to drift a little bit. So it's not just a constant offset; they actually are drifting a little bit up and down too, which is not really what you want to see. It appears to be a bias, but it's basically hard to prove and fix. So we've been playing a little bit with calibration as well. So different folks have some upstream calibrations where they can play with the input radiances, reflectances, and and we've tried a few of them. And we do. This is our C6 data or C6.1 with these offsets, and we can try some calibrations and get a little bit closer. And so so that's interesting. Anyway, so the summary of where we are in collection 6. We have this derived optical depth from both Terra and Aqua, but Terra is a little bit biased high. And we still say that some people ask us and say, can you not use Terra's AOD anymore? And we say, no, that it's for many applications, it's still, it's still going to be perfectly fine, but we're still working on the calibration. And there is now a MODIS collection 6. So this started last year, which was motivated by something completely different than our need. It was motivated by some instrument degradation and other channels that are unrelated to the aerosol retrieval. But that made us make a few changes to our algorithm, and I'll show one of them later. What I didn't mention before is our standard product is 10 kilometers. So it's but we also have a 3-kilometer retrieval, which was kind of asked for by kind of air quality folks that needed more kind of neighborhood or interested in higher resolution. And also that, so I've been telling you this whole time about the dark target product, which is what we do. There's also a deep blue group. There's another group that's also doing retrievals as well. They call themselves, and they're using a different method, a different algorithm, and they rely more heavily on the deep blue channels, which is a 412 micron channel for MODIS, and they can do some retrievals over more desert areas that we don't. So there is a merge product there. Additional thing that we have is urban improvements. So what we had found in collection 6 is that if you knew something about the urban area, like more cities, we'd find that in city areas we'd had a high bias to our retrievals. And it was all because the cities don't behave like the rest of vegetation or natural surfaces. And so by making a simple correction, Pawan Gupta, who was in our group, was able to basically, instead of having this high bias over urban areas, urban percentage meaning so that 100% would be a completely urban area in that pixel, that he's able to reduce that bias. And so that's in our algorithm as well. And so, yeah, currently 6.1 has been run. You can get all the data. It's been reprocessed. It's and everything is available for use. And so my interest has been with this is, okay, so we have these two instruments. We have two MODIS. We do have some discrepancies between Terra and Aqua. They've actually lasted, again, we started in '99. They were originally supposed to be maybe a 5 or 7 year project. 5 was the nominal mission, 7 was expected. But it's been almost 20 years since they were launched. And so as you saw, there's some degradation that's happened over time. But we want to make now a long-term record. And so the GCOS, the global community on global climate observing system, that's what it stands for. They have come up with some parameters that are required for climate data records. So optical depth, aerosol optical depth is one of their requirements. And what they suggest is that horizontal resolution globally should be 5 to 10 kilometers. So we kind of are there. Accuracy, max of 0.03 or 10%. Well, we're kind of close. We're 0.04 or 10%. We're getting pretty close. Stability is a little in question because we saw there's a little bit of drift in the Terra versus Aqua. And then the other requirement, which we obviously don't make from 1 overpass per day or even 2, is a temporal resolution of every 4 hours. The other part is that it requires a multi-decade record. And so, yeah, we're almost at 20 years, but 30 years or more would be better. And so that's what we do. So we've been looking beyond MODIS for a while, kind of, hoping that MODIS won't go away, but it's, it might. And actually, this is a little older. It's more than 17. So we're almost 18 years of Terra, and Aqua is almost 16. And so the thing we look forward was VIIRS. So VIIRS is also, it's run here. It's a NOAA-NASA joint work, but NOAA has been working with the algorithms, so like ISTWAN over here and others. And what we decided is even though they're really good, and for many applications, that if we were trying to make this long-term record, that the NOAA products are probably too different from MODIS. And so we went ahead and said, can we port the algorithm almost exactly as we can? So here, so these are the wavelengths from MODIS versus VIIRS, and you can see the wavelengths are a little bit different. MODIS has that 36 bands, and then certain numbers of them are in these visible and near-infrared channels. And then what I put on the back here was different land surfaces, like you can see deciduous, conifer, seawater, and just basically just showing that you have to adjust a little bit for the new wavelength bands and surfaces. So we did that as best as we could, and we then ported it to VIIRS, and we're getting essentially the same statistics as we do for MODIS. A little bit noisier, and one reason we think is because we're doing a slightly higher, we're doing the number, so MODIS we do 20 by 20s to get 10 kilometers. Here we're doing 8 by 8s to get 6 kilometers, so we think it might be a little bit noisier just with the signal to noise part. But it's still pretty good. And so now we ask questions. Well, we have 3 of them now. There's something about give a man a watch. He knows what time it is. Give it 2. Now he's confused. You don't know what time it is because it'll be different. And 3, wow. But it turns out that VIIRS, when we run our VIIRS, it works out pretty close. We do get again an offset in a very similar way that we got from Terra versus Aqua. And our histogram is a little bit different. And we're still exploring, again, is it calibration, or are we doing something wrong, or whatever. But we're trying to, do the best we can. And if this works, and we then can port it to other sensors as well, and then really get the 30-year plus record that we're after. And this is just kind of the time series too. This is Terra versus Aqua. This is the VIIRS versus Aqua, and these are again collection 6. We expect the collection 6.1 will, from MODIS, will still have the same. Oh, we're completely out of batteries now. We'll have, again, the same kind of, yeah. Oh, that's fine. It's amazing how these look like real Energizer batteries, though, so they'll last forever. Oh, they don't seem to be any more live than the other ones. Oh, well, it's still working, though. Even if it's blinking, it's still working. So, again, we went through more details. You know, this is what we got on the outset. We're also trying things that we really got interesting, too, is there's slight differences between these wavelengths in even gas absorption. So this is a water vapor continuum line on here, or water vapor lines on here. And even though MODIS and VIIRS are almost identical in terms of the center wavelength here, they do have slightly different spectral responses, and so they cover a slightly different part of the absorption of water. And so, you know, we were basically interested in that and wondering if that could be some of the differences that we see. And so there is at least one study out there, and I think there's other studies as well, that, you know, basically say that you go through all this exercise and that maybe we have to multiply. If we wanted them to be completely, perfectly aligned, we might have to multiply, you know, to normalize the sensors to each other. You might have to, you know, do something like make, I guess it's not working at all now, you know, multiply VIIRS by 0.97 to get something that's close to MODIS. So I'll use this thing now. I'll use the computer. And so we have we still don't have a product yet from VIIRS. We were hoping that we would, and actually we've kind of run into funding issues, and so we haven't been able to completely port and make our routine archive product for VIIRS, but we certainly hope that we will get to that as soon as we can. And then these are just the differences that we would expect from the different kind of products, even if they are as consistent as possible. And so we're working on a paper based on that. So one difference is again, the product resolution, the granule size. People that are using MODIS will have to use different formats for VIIRS, et cetera. And so again, our goal has been trying to get this consistent global aerosol using dark target. Try and get something that's along the purple line in the middle here that's as consistent as possible, even if the individual sensors are diverging a little bit. So where are we at? So now we're going back to comparing the GCOS requirements. And basically the big red line there is still the 2 times a day. So everything else is getting kind of close to what we require, but the temporal resolution still needs some work. But we'll get back to that in a second. Let's look at other things that we're missing. And one is heavy aerosol events. There's a lot of, when we do these retrievals, and I showed you how there's cloud masking, and there's a whole bunch of selections that say we're not going to retrieve under certain situations. One of those is these extremely heavy scenes, like with this ridiculous amount of aerosol. And one is like this one case is the Indonesian Fires of 2015. So there were fires everywhere. Turned out there were some this aeronet, the sun photometer at the ground. Remember I said that 1 or 2 was a pretty polluted day. They were measuring almost 7 optical depths of almost 7. The sun completely obscured in the visible wavelength. You can't see the sun just from aerosol in these areas. But it definitely wasn't clouds. These were actual smoke. This was actually smoke. And none of our systems, none of our retrievals, and even aeronet had trouble retrieving or measuring this stuff. So just to plug in that aeronet itself has a new algorithm and data set, which they call version 3. And so earlier look, I can use the mouse now instead of these things. That's cool. So this is version 2 over the area in Indonesia, and they had almost no retrievals, no measurements of these high optical depths. And that was because their cloud masking was so strict. Now they have a new way of doing it. They realize they're not clouds, and now they have these extremely heavy aerosol optical depth measurements in this site in Indonesia, and now they're in the data set. So we know they're there. How is it going to, so studies, questions that we had is saying, if we could retrieve it ourselves from the satellites, how would that eventually, enter into making estimates of climatology and radiative forcing, and also if you had air quality models or anything else that needed this. So Ying Chi, who's in our group, it just was submitted, and I think she just had to make the corrections so it'll be available in ACT. She's basically finding that you can, doing something smart. This is our old retrieval. We missed all the smoke, and then she's found a way to relax some certain thresholds, and therefore we can actually measure and retrieve the AODs in this case Singapore for this time period. So you get a lot more measurements now. Another thing that, oh gosh, I guess that didn't work. But another thing we've been trying to do is understand, we have these kind of expected errors, and they're always compared to AirNet, some other, we're always comparing to something on the ground. But something that we've been trying to understand and do is to get some sort of more quantitative uncertainty in our data products. So doing things like Jacobians, doing things like, what is the change in optical depth for change in reflectance, so trying to include that into our product. And then a thing that we've been having a lot of fun with lately is looking at distance to clouds. And so if you now have this, n by n box that we have here, and we have some clouds that are identified, well, could we do anything with the fact that certain pixels are close to clouds and certain pixels are far from clouds, and then maybe make multiple retrievals and do some kind of ensemble thing. And so that was what this was supposed to be, this fuzzy picture, and it's basically showing that close to clouds it could be anything, and maybe there's some misidentified clouds or things that are contamination that's creeping in. But as you get farther from clouds, it becomes more stable, and you can get a sense of the statistics in your region. And then again, so we're still stuck on this temporal resolution part. So now we have, what's missing? Multi-day. There are places in the globe where there's a definite diurnal cycle. These are so taking optical depth at noon. This is the relative change as a function of day. It's in this case Mexico City, and so optical depth and angstrom exponent. And so just by taking one or two measurements, let's say Terra here and Aqua here, is not going to give you that diurnal signal. It's not going to give you that information. And so now we have the geo stuff. And I took this off of the NOAA products, and it's fun to see this movie of, this was a particular case, September 4th, 2017. This is the ABI, which is the Advanced Baseline Imager instrument on GOES, on the new GOES. And so they have their own retrievals as well. So they're doing optic aerosol as well. They have operational products. And it's just amazing because you can see things move. You can see a time of day. And so now we're looking into this as well. Can we, doing it again. I guess I need to go to the next slide. But it's amazing watching the time of day. And so I first just show the RGB, the visible image, and then these are the retrievals on top of it, and you can see how things are moving over time. And it's fun to play with this site, this aerosol watch site. It's called Aerosol Watch, and it's really good. So now we again, from our perspective, we have the 17 years of Terra, the 15 years of Modus on Aqua. We've been working with VIIRS. And so, can we port, the same algorithm to the GOES data, the Himawari data, which is a similar kind of geostationary sensor that's from Japan and over East Asia. And we've also been playing with the EPIC instrument, which is it's an instrument 1 million miles away in L1 point. We haven't gotten nearly as far with that, but it's been fun to play with. And so what's great about these is now we have a consistency. Here is Modus, here is VIIRS. We do have to make some shift. The AHI, which is Himawari, does have most wavelengths that we care about, although it's missing a couple. And then the ABI also has most wavelengths we care about, but it's missing a couple. So we can live with that, and we do have to work. We have been trying to work out some of these details, how to compensate. And in the end, we'll report AOD at 550 for everybody. So we'll report optical depth at the same wavelength for all sensors, and then otherwise do the best we can in terms of doing the same consistent things of cloud clearing, about doing pixel aggregation, and make the same kind of assumptions we've been making everywhere. And so what we've been trying to get is now we start putting all these things together. We have the GOES over the U.S. We have the Himawari, and then we have, let's say, the two MODISes and the VIIRs. And so we can make these snapshots perhaps at at a particular UTC. So that maybe this might be only at 3 UTC, and then make another snapshot at 4 UTC, and then so they can be easily compared with models that will do that as well, global models that also will be at 1 or 2 or 3. And something else that I thought would be fun to do is what's interesting about these is that depending on where you're observing, it's a different time of day. So maybe this is whatever 12 UTC, but because of the local time, because of it's looking far off on the limb, it's looking at a different, it's actually a different local time. So I think I would like to try and re-aggregate things so that you have the statistics of local time that you could then think about, what is the global diurnal cycles of things. And so we've been now lucky enough that we've been able to take the same image that we had from the aerosol watch, and we've been able to retrieve our own retrieval algorithm. And we haven't done comparisons yet, but overall it's going to look pretty similar. We have a different, we're going to have, again, different thresholds for what we're going to retrieve and not to retrieve. But hopefully this will be consistent with our long-term record of MODIS and VIIRs. And so we can see, how has, what does 10:30 a.m. look like over time? What does 1:30 look like over time? And then also, the applications that really need time of day as well, quick time turnaround. And then so, our first attempt at this was not so successful, but this is AHI, this was ABI, and then this is MODIS as well. And a couple of these other ones, but again, we're trying to get at a particular time. So yeah, so we're just getting started with this geostationary. My group mate likes to call it breaking the temporal barrier. It's fun with that, but again, we only have these 2 observations we made from Terra and Aqua, and now we have the opportunity to see the rest of the day, and also look at both our history for time of day, that we the 10:30 versus 1:30, and also any of the applications, air quality, et cetera, that do need aerosol and much higher temporal resolution. So I'm almost done. A couple more things we've been playing with are what happens at the really high resolution. So we have some both airborne campaigns that actually, it's essentially the same instrument as MODIS, but it's called the Enhanced MODIS Airborne Simulator. And instead of 500-meter pixels that MODIS is supplying, it's actually providing 50-meter pixels. So we can look at aerosols at very high resolution, and also, let's say, next to clouds. And more recently, we've also been playing a little bit with Landsat data. I don't have any plots to show. And then the Europe Sentinel-2, which is essentially Landsat Light 2 as well, and seeing what we can get out of that. So looking at using the same algorithms and same retrieval techniques, but looking at the really high resolution. So just this one case here, we're doing. We just submitted a paper, but this was the EMOS looking at on August 30th. It happened to be over the U.S., measuring over the U.S. Here's our retrieved optical depth, and we've been comparing with a LiDAR that flies right in the middle of the. So the LiDAR is flying right in the middle of the scene, which are these black dots here. And so we were kind of looking at. What we've been interested is that. As you can see, there's a really large gradient of optical depth between places that are far from cloud and close to cloud. And in a MODIS pixel, which is a 500-meter pixel, and we're doing 10 by 10 averages, we're pretty much going to throw most of this out. And we're going to get, because there's clouds everywhere in here, we're going to throw most of this out, and we're only going to get retrievals in these in these areas far from clouds. And so at this resolution, we start to look at, what happens, closer to the clouds. And and so right now it's still pretty experimental, and so the LiDAR is basically saying, well, yes, there's clouds here, 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 and here, and here. And we're asking the question, if we're looking at a LiDAR is basically measuring directly, like our normal remote sensing is using reflected light at, reflected solar radiation to infer our optical properties. A LiDAR is doing it a little differently. And so, if they show us exactly the same thing, then we know that that what we see from the remote sensing from a satellite or this aircraft is consistent. But what we were actually seeing is that there is the gradients that the LiDAR is seeing, if you try and integrate and get total aerosol properties, is a little bit different than we were getting from the remote sensing from MODIS or MODIS-like. And so it's basically giving us questions about things like, are you getting extra scattering from clouds? Are you getting cloud contamination? Things like that. So it's still pretty new, but it's been fun to play with. And so we have our kind of now dark target family. We have the suborbital work, we have the LEO work, the low Earth orbit, MODIS and VIIRS. We have the GEO work that we're working with, and then hopefully we can play with it beyond. So we have this whole, looking at a long and wide consistency in algorithm and product. Another thing that Colin's working on, who's in our group, is trying to make this connection. Again, this is definitely more of the air quality focus. He's got a citizen science project that he's working with. So now we have people out in the field measuring aerosol on the ground. And I didn't talk about this before. Again, our whole job from the satellites, we're looking at column optical depth, column aerosol. And if you're in air quality and you want to worry about what you're breathing, what we really care about is the stuff at the ground. And there are a lot of studies that trying to connect the total aerosol, the total column, to the stuff at the ground. And it's really tricky. It's not very straightforward because of differences in aerosol levels. Aerosol isn't always at the ground, and there's vertical profiles that must also be important as well. But one way to get at this a lot more, and to get a lot more statistics of the ground versus the total column, is to have people out there. Like there's already ground sensors, EPA, but they're fairly spread out. And so his idea was now you have some people using low-cost sensors. And so that's what this project was about. It's just trying to connect the satellites to not just the measurements, but also the people who could get into this, get into it because they're now in charge of their own measurements. So just showing that it's part of what we're doing as well. And so now we have these sensor deployments all over the place. And I'm not going to go into the details of the sensors at all, but it's kind of a fun project where we're getting people involved, who are making measurements and also, coming to workshops and trying to make some science understanding of how the ground and the satellites match, but getting people involved in that as well. So we have this long and wide aerosol climatology. We're trying to do it all from this kind of, basic but pretty simple algorithm. It's maybe not as global as we would like, but it can work on lots of different sensors. AOD is one of the essential climate variables that we want to measure, and with things like MODIS, we can get sort of this global view. If we stitch together MODIS and VIIRS with the same algorithm, we can get the long time series. And now and I didn't talk about it, but if we could get more data from Euro and Asian sensors, we could increase this more. With the GEO, we'll get some of this time dependence, and then the fine tuning of algorithms, we can get some more of the with radiometric calibration, really work on that hard, we could get this climate data accuracy and stability that we would like. And of course, we're not the only ones doing this. There's other groups as well. In deep blue, the MIAC algorithm, which is also a Goddard algorithm. Groups doing work here at NOAA. I've been, and so, but doing some of the work on a local scale with citizen science and et cetera. So just the last couple things, just that, it's not just our algorithm, it's not just dark target, is now we're trying to also look at other, other combinations as well. So, one is we realize that we do have to use other sensors to help us, let's say, do that that case of very, very heavy aerosol. We did need other sensors to kind of tell us when it was a cloud, when it wasn't. And so in this case, we're using OMI, and OMI was traditionally an ozone monitor, also used, but gets aerosol. It measures in the UV or closer to the UV or in the UV, and so work that I'm sort of affiliated with, but people in our group is working with PACE, for example. PACE is a phytoplankton aerosol cloud and ocean ecology work. And so now, can we now join MODIS and OMI and get something that is not just telling you the size and the optical depth, but something more about its composition and height and et cetera. So just kind of relating that we are working on other stuff for the future as well. And that's pretty much it that I have. And we have a website that we have a reference for all things dark target, and then algorithms, some samples, validations, et cetera. So continue to ask questions and et cetera. So thank you.
Thank you, Rob. The floor is open for questions. In the back.
Right. Yeah, that's something we would like to. Once we're pretty confident on doing the consistency, then we have enough data to compare with. I think that's something we would like to do, is to, now we have the geo at 1030 versus the 130. How different are they? I'm sorry? Commercial applications? I don't know. I don't know. Anybody have good ideas on that? I can't think of commercial. I'm sorry? Oh, okay. Yeah, I mean, but commercial. I'm trying to think of commercial. I guess people can find money in anything, I guess,
So given we talked about the cloud contamination and also there will be office drift. So is it possible or advisable even just to look at trends in the data set now? Now you got 15 years.
Now we feel like, yeah. So people are definitely doing it, and that's why we work so hard on trying to understand them ourselves. Is that, yeah? I think we're almost to the point where I think we trust our data well enough to do trends. With this last collection, 6.1, there's still the offsets and MODIS, but they seem, at least through 2017 or so, they at least are trending together, or whatever it is they're both doing. They're both pretty much doing the same thing. So then we have a little more confidence that either one of them is doing it right. But there's places, most of the globe, there seems to be, if you actually do a trend, most of the globe overall, there seems to be no trend at all. But there's definitely places, like east coast of the U.S. that has a consistent downtrend over the course of the years. Places like the part of the Indian Ocean seems to have an upward trend, and places like East Asia seem to go up and down and up and down. It's not been totally consistent. But definitely after 2008, it went down very, very, very strongly.
So you showed a heavy aerosol.
Mm-hmm.
Is that a case study, or you can apply globally?
So that's so far as a case study. We were trying to apply it globally and seeing what it does. Most places it seems to work okay, but there are a few places where it doesn't. So
my understanding, key part is
key is cloud mask. It turns out, I didn't go into details in this case, but it turns out the problem was not the cloud mask in this scene. The scene happened to be, so I think I described in the beginning where we have water, where we have land versus ocean. And something we do is to make sure we don't have accidental water over land. We do an Ndvi test. And so if the Ndvi, which is a comparison of red and near infrared channels, the index goes below 0 or close to 0, then you think that it's definitely not a vegetated surface. And we use this to flag out inland water. And it turns out this heavy smoke also gets you close to 0 in Ndvi, and so we were throwing it out because we thought it was water.
What is the cost? You said some global and sometimes fail. Why it fail?
In this, well, for heavy aerosol, often it's because of any number of reasons. One is the Ndvi going below 0. Another is sometimes it gets thought of as a cloud, and it turns out so DMC is also working on Beijing area. And that area, in the wintertime, it's got this very low level, very dense aerosol, and it sometimes gets flagged as snow, like it looks like snow. And there is snow sometimes, but it doesn't seem to be as much snow as it. And so that's another test that we're trying to see, that we have to see if we can make it global, because there's a lot of stuff in Beijing that we would like to measure. It's very difficult and global. So I mean, yeah. But at least you get an idea of what you're missing, right? You may not know it globally, but you can now do these case studies and piece together and say, okay, we missed all this in Indonesia, we missed all this in Beijing, and how does that now enter into understanding our global statistics, et cetera?
So have you or any of your colleagues conducted studies on the relationship between vegetation cover and aerosol?
Yes. Absolutely, yes. Feedbacks, I have not done that kind of stuff, but particularly what? Dust lofting, yes. I mean, so yeah, definitely related to surface type and change, especially also changes in time. If a lake becomes dry or anything else like that, things can change over time. But also we also recognize that some of our biases that we do have are related to surface type as well. So that's a separate problem, but it's also important.
For the relationship, there has been like empirical studies on the relationship between.
Yes. Yeah. Exactly.
So what specifically do you do with the calibration to try to reduce the difference between?
Yeah, different. Well, in most cases, we don't actually do that much with the calibration because it's not really our thing. But there is groups that are looking over looking over desert targets, looking over clouds, looking over places where they expect to be very there's different kinds of comparisons, some vicarious calibrations, et cetera, that could be used. And so so we're trying, maybe they're coming up with some numbers and we're trying them, seeing how they work. But it was actually, from the original, so I showed collection 6, it was collection 4 and 5 data, like earlier data, that we realized that there were some huge differences between the Terra and Aqua, which was enough that when we showed that to, again, calibration type folks, they're like, oh, wow, that's interesting. And so us finding that originally was kind of how some of this started, was seeing these discrepancies over time. And some of it's spectral.
Are they identical?
They're close. Between Terra and Aqua, they're really close. There is, but there are a few channels that are a little bit different. But they are very, very close. But but things have happened. You know, the instruments, you know, are different ages. One's a few years older than the other. They've been in space at different times. They've experienced different you know, different solar activity, different whatever, and so they've degraded at different rates over time.
I know there's another company, but
Yeah.
maybe we talk after that. But
Yeah, that's fine.
I want to give Rob another round of applause.
Thank you.
You'll feel better.
Thank you. Thank you.
Let me ask a quick question. So you have cloud, if there's 10 by 10.
Mm-hmm.
If there's cloud, you treat it as, how do you treat it? If there's one pixel cloud, 10 by 10.
Yeah, I mean, as long as there's some clear pixels, we'll go ahead and retrieve.
Retrieve pixel by pixel, right?
We'll retrieve, so if here's your squares on here. Like,
Yeah.
let's say this one's a cloud, like we have 10 by 10 box.
Uh-huh.
Maybe we identify cloud. We'll keep the ones that are clear, and then do
You retrieve
on the clear one,
then,